So far, we have talked about many optimization algorithms, including gradient method and the Newton method. And all these methods are based on the one simple assumption that the parameter space is Euclidean. So especially if we focus on the gradient descent method, then the direction d star can be obtained by this. So we have objective function, and then this one is a current parameter. So we are at this w, and we want to add some direction, which is gradient usually. And then with this constraint, we want to find the best d. When the objective function looks like this in the two-dimensional space. So we have w1 and w2. Okay, so our parameter is two-dimensional, and we have loss function here. And then when we are here, w is here, and then our function, the loss objective function value is here. And when we update the parameter, actually we'll look at this area. So within this area, we want to find the best parameter. Then this one is going up, so probably this one. The next w will be around here. The norm of d is bounded by this epsilon. When we have this boundary, then there is no constraint about this. I mean, the parameter space is just Euclidean. That is what we did so far in the gradient method and the Newton method. And in gradient method, we just approximated this objective function with the linear equation, and then we follow that direction. And in the Newton method, we approximated this objective function with the quadratic equation. But about the parameter space, they have a strong assumption actually, which is Euclidean. But the direction should be taken in the space of all possible likelihood. So in this case, we didn't talk about any distribution, likelihood. Let's say w is here. What if when we move to this direction and the likelihood is quite small? Then that is not a good direction, probably. So we have to think about this distribution, so likelihood. So let's take a look at this figure, which summarizes the difference between the parameter space based on the Euclidean geometry and the parameter space based on the likelihood. In this figure, look at this distance between w1 and w2. Okay, let's say this one is d. In the right figure, they have the same kind of distance from w1 to w2, but look at this distribution. P x given w1, and this one is p x given w2. And this one is p x given w1, and this one is p x given w2. So in this figure, when we move parameter from w1 to w2, then this distribution is moving slightly. If we calculate the Ka divergence between these two distributions, then it is quite small. But what about this one? So even though the distance between these two parameters is the same as this one, when we calculate the Ka divergence between these two distributions, then definitely this divergence is way much larger than this one. So the point is that even when the distance between two parameters are the same, but when we check the likelihood here or here, this divergence between the two distributions might be quite different. Natural gradient argues that we have to consider this situation. So we will take this likelihood divergence into account. So as I said, in terms of K divergence, the left figure has a lower divergence. So although they have the same difference in the parameter space, the differences are different in the distribution space. Okay, then now we will talk about the natural gradient. So parameter space might not be Euclidean. That's the problem of gradient method. So gradient might not be the steepest direction, but natural gradient is the steepest direction. And when the parameter space is Euclidean with gradient g, then update rule looks like this. Okay, I think this is already familiar to all of you. This is a gradient method, and when we check the norm of this update, then this is the amount of update in the parameter. But when the parameter space is non-Euclidean with the gradient g, then this should be like this with this Riemannian metric. So when we have a globe like this, here is Korea, and around here, let's say there is Argentina. Then what is the shortest path from Korea to Argentina? Definitely this is not the shortest path. We cannot go through this globe. We have to follow this sphere. If it is Euclidean, straight line is the shortest path. But we are living on a non-Euclidean space, so when we check the distance, we have to calculate this. So to calculate this distance, we need this Riemann metric. Okay, so let's just accept that. When we calculate distance on non-Euclidean space, then we need this Riemann metric. So in that case, update rule should be like this. And this one is familiar to you in a sense. Like this one looks like a Newton method, right? But there is a big difference between this natural gradient and the Newton method. In the Newton method, we have a function here and the parameter, and we actually check the shape of the function based on the second order derivatives. But in the natural gradient, we are not talking about the shape of the function. We are talking about the shape of the parameter based on the likelihood distribution. And the Riemannian structure of the parameter space of a statistical model can be defined by the Fisher information based on the information geometry by Amari. Now let's drive the update rule of natural gradient. Okay. Instead of using the Euclidean distance, we are going to use K divergence. This is the only difference compared to the conventional gradient. So we use K divergence rather than Euclidean distance. In the Euclidean distance, we used like such that d is smaller than epsilon. This is what we have in the conventional gradient. But in this natural gradient, we have K divergence. So when we update the parameter from W to W plus D, then we check the likelihood, and then these two likelihood should be close to each other. So K divergence should equal C. So in this case, D should be within this boundary, within this ball. But in this case, when we update the parameter W with D, then the change of this likelihood should be a constant. And then, as you know, we can use Lagrange multiplier, lambda. This one is what we want to minimize, and this one is the constraint with the Lagrange multiplier. Now, this one can be approximated by this with the Taylor series. Okay, we can accept this part, and this one is coming from this one. Then what about this one? So this K divergence between these two can be rewritten by 1 over 2 times lambda d transpose f d. We have to prove this part in the next slide. Okay, but let's just assume that this is what we have. Okay, then we can take a derivative of this objective function with respect to d and set it to 0. Then this one is 0 because we don't have d here. So when we take a derivative, this one will be 0. And this one, when we take a derivative with respect to d, then this one doesn't have a d, so this one will be 0. And now we have a d here, so when we take a derivative, then we will have this part. So we have here. And then this one is square of d, so it will be lambda times fd. So this one is what we have after derivative, and then it should be 0. Okay, so we got this equation. And then d can be rewritten in this way. So this one is a conventional gradient direction. And then this one is about the Riemann metric or Fisher information. So the direction in the natural gradient is like this. As I said, this one looks like a Newton method. The Hessian is about the second derivative of the objective function, but in this case, f is the second derivative of, we will see that, but the f is second derivative of the k divergence between previous likelihood and the updated likelihood. So, given a loss lambda parameterized by w, by a constraint that the amount of change is constant in terms of k divergence of likelihoods before and after taking the step. This is how we derive a natural gradient. And then learning is locally robust reparameterization of the model, because likelihood does not depend on the parameterizations, which means when we have a parameter w, if we redefine this w into like 2 times w, so this is reparameterization. And even with these reparameterizations, the likelihood is not changing, so it's robust against reparameterization. But in conventional gradient method, think about this one. So in W1 and W2, and if we change this W1, so if we multiply this W2, then we actually change the shape of this function. Then the steepest direction might change. But in the likelihood, if we change W, let's say W is W1 and W2 in two-dimensional space, if we update this one, if we reparameterize this one into W1 times 2 and W2, but still the likelihood is the same. So that's good. And another one is that the KL constraint avoids overfitting. So when do we have overfitting? Usually when we have sparse data samples, and then when we fit a model to that sparse samples, then probably we will have overfitting problem. But in the natural gradient, we have this likelihood, and then we preserve this likelihood. So when we update the parameter w, we don't actually change this likelihood that much. So still we stay in the likelihood kind of situation, which means w is not moving toward some outliers. Okay. But in conventional gradient method, when the direction is wrong and then it's possible to move toward outliers, likelihood of w t plus 1 might be really unlikely. In that case, probably the model can overfit. But in this case, with the k divergence constraint, after updating, this one is quite likely because we don't change too much. The divergence between these two is quite limited, so we don't move toward outliers that much. It's not possible. So natural gradient can avoid overfitting problems. So it learns fast because W is moving around with a high likelihood. Actually, when we do some experiments, then the natural gradient learns fast, converges faster than conventional gradient. So now let's prove this K divergence and the Fisher information. So in this slide, okay, this part becomes this one, and the other part is just straightforward, and then let's just focus on this one. The K divergence between the previous likelihood and the new likelihood can be rewritten as this. So we want to prove this one. And in the previous slide, we said that this is the Fisher information. So we want to prove this K divergence is the same as D transpose Fisher information times D. So when D goes to 0, so when we update the parameter just a little, then the D goes to 0, okay, then the KL can be approximated by Taylor series again. So this is K divergence, and then this one is Taylor series, and this one is obviously 0 because we have the same likelihood. And this one is a little tricky, so in the following slides I'm going to show that this one is actually expectation of gradient of log p of x given w, and then this is a 0. I'm going to prove this one in the following slides. And then we have the third term. So this one is actually approximation, which means we have some other terms, but we just approximate ignoring this part. Okay, now this h is the second order derivative, like this, which means h is a Hessian of this Kullback-Leibler divergence, not the Hessian of objective function. And then to prove this, we have to show that f is h. So we have h here and then we have f here. So if h is the same as f, then since this one is 0, this one is 0, then this term is the same as this term. So we prove this one. So f is here, so we have f and we have h. Okay, now we're going to prove this equation. And before proving that, we have to learn some concepts. Okay, so we have to understand the score function. And score function indicates how sensitive P is to W. If the score function is high, then when we move W slightly, the P of X given W moves a lot. So it is defined by the gradient of this log probability. So we can use this notation or this notation. Basically the same thing, but this one is simpler than this one, so I'm going to use this one. Then expectation of this score function is 0. So we want to prove this one because this one is another kind of popular pattern in machine learning. Okay, so I hope you memorize this proof. This one is a score function, and this one is expectation of a score function. And if we rewrite this equation, then we have a probability and a score function and integral. Okay, this is just the definition of expectation. And then look at this one. From the score function, we have this one. How can we do this? I think you are familiar with these terms, so let's use this one. When we take a derivative of log x with x, then it is 1 over x. Okay, then instead of just x, then we have another function. So if we have derivative with respect to w, then we have 1 over p, then we need pw. So this one is actually this one, the same thing, and then we have this one. Okay, so from this score function, we can have this one. So in machine learning or deep learning, you will see this kind of pattern a lot. We have a score function. Sometimes we want this one, or from this one, we will use this score function. So they go back and forth, okay? And then we can cancel two terms. Now we have this one. And then we have integral and the derivative, and they are independent. So the derivative moves out, and now we have derivative. And now we have integral here. And this one is 1, because if it is a probability, then it should be sum to 1. Okay, so no matter how you move this w, this one is always 1. So derivative will be 0. So the expectation of score function is 0. Now we want to talk about the score function and the Fisher information. So we will see the relationship between these two. Okay, the variance of the score is defined to be a Fisher information. So if you look at this one is the variance of score. So this one is the derivative of log probability, and this one is another derivative of log probability. And this one is actually measuring the amount of information that x carries about the w. Okay, then this gradient is talking about how much it is changing. This is just a conventional objective function. Then the derivative tells us some information about the shape at this moment. Likewise, this one tells us how steep or how flat the distribution is changing depending on this change of w. So let's accept that this variance of score is defined to be Fisher information, measuring the amount of information that x carries about w. And then it is the same as negative expected Hessian of log likelihood. So we want to prove this one. So the variance of score is the same as negative expected Hessian of log likelihood. Okay, so let's start from this one. So we have a Hessian of this log likelihood. And then, when we have g and f, so when we take a derivative, then it is g dash times f plus g times f dash. Gradient of log p x w was gradient p x w over p of x w. So this one is first derivative, and then we have one more. So now we have to take a derivative to this. Then, as I said here, when we have two functions multiplied, then we have to apply this rule. So in this case, we have one function and then another function here. So if we take a derivative here, then we have this one, and we just multiply this one like this, and then we have next one. So we have to take a derivative to this one. So this one goes here directly, and then when we take a derivative, then we have this one. And then if we focus on this one, then we have the same term here. And then here we have a square here. So if we focus this one, then this one is this term. And then when we focus on this one, we have this term. So it's the opposite directions from the previous slide, like this. So this one is coming from this one, okay? And then this one looks like this one. Okay, then now we want to take expectation here. So if we take expectation here, then this one we have a probability and this term as it is. And then we can cancel. Now we have this term. And again, this term is independent of this integral, so this one goes out. Then this one is 1 and this one is 0. Okay, so when we take an expectation, this one becomes 0. So when we take expectation here, which is exactly the same as this one, and when we take expectation here, we have here. So this one is exactly the same as this one. Okay, so in this slide, we prove that the variance of score or the feature information is negative expected Hessian of low likelihood. We have the final slide. Okay, so let's focus on this K divergence. Then this K divergence can be rewritten in this way. And when we take a derivative, then it is like this. Because in this term, we don't have W. So we have only this part. Okay. Then when we take a second derivative, then we have a second derivative here. Okay, so in the previous slide, we had this one. So this feature information is the same as a second order derivative of low likelihood. And here, the second order derivative of K divergence is negative expected Hessian of low likelihood. So combining these two, then now we have this one. So let's go back to this one. So from this K divergence, then we got this one. So from this one, then we got this update rule for natural gradient.